Okay, so for the next part here, we will talk about some experiments used to determine the enthalpy change. Now, we know that we are so interested in finding out the enthalpy change of a reaction. So this is how we can do it. We will do something called calorimetric experiment. Calorimetric comes from the word calories, and you know calories is a unit for energy. So calorimetric experiment is an experiment used to find out the heat change and therefore the enthalpy change. Now, usually the heat change, after we find out the heat change, then we will use the heat change to calculate the enthalpy change in terms of kilojoule per mole, because we are so interested in the quantity of reactants or products associated in this experiment. We want to, at the end, standardize it into per mole so that we are able to compare the value easily. Okay? Now, first of all, the heat change represented by Q. You know this equation very well because you learned about this in Form 3. Q equals to mc delta T. Now, there's a little bit difference between physics and chemistry, but so that's why I will break it down to you some of the usual units, some of the usual consideration when it comes to calorimetric experiments. Now, first of all, Q is the heat change. The unit is joule, not kilojoule. In physics, you may use kilojoule more often, but here in chemistry, we will use joule. Now, you know that heat is a scalar property, basically means it must be positive. So whenever you do this calculation, you must get a positive answer. But you may be able to tell from the temperature change that whether it is exothermic or endothermic. Okay? Anyway, make sure it is positive. You don't have a negative heat. Now for mass here, pay extra attention is that first of all, we use gram instead of kilogram. And secondly, and most importantly, the mass is referring to the substance where we measure its temperature. In our calorimetric experiment, usually it is water. It is water. So very often, students will take the mass of the reactants rather than the water because they may feel like, oh, I'm determining the enthalpy change of this reactant. But think about it, like mc delta T, the delta T is the temperature change of the solvent of the surrounding, right? And you think about it, the mass here should also consistent with the temperature change, right? So we are concerning about the substance of which the temperature is measured. And most of the situation, the mass is referring to the mass of the water. The reactant will be consumed, right? So if this is the mass of the reactant, then after the reaction, the reactants are all gone. Then how can you measure the temperature of the disappeared reactants, right? So bear in mind, the mass here, usually we are talking about the mass of the water, okay? Of course, this is not necessarily water. Sometimes it could be other substance, but 9 out of 10 situations, it would be water. So bear in mind. Here, C is the specific heat capacity. In chemistry, we will use joule per gram per Kelvin, and basically it means that the heat required to change 1 gram of a substance, usually water, by 1 degree Celsius. Okay? Now, because water is often used, and water has the specific heat capacity being 4.2 joule per gram per Kelvin, or 4.18 joule per gram per Kelvin. Okay? And sometimes we use heat capacity instead. Basically, heat capacity, this term, this capital letter C, already include the mass of the substance. So instead of putting down Q equals to mc delta T, we can simply put down C delta T. Okay? And temperature change is either in degrees Celsius or Kelvin. It doesn't matter. But bear in mind, temperature change needs to be a positive value. The reason is because, like I said, here, Q must be positive, right? And you know, mass must be positive. C must be positive because it is a constant, 4.2, right? So delta T here must be positive in order to make the Q positive. So But then you know that some reaction is exothermic, which makes the surrounding hotter. Some reaction is endothermic, which makes the surrounding cooler. So how can we make sure we always get a positive delta T? Very simple. Higher temperature minus lower temperature. Okay. Some textbooks, some tutors, they may say that, oh, you need to do like a final in temperature minus initial temperature. But if that is the case for an endothermic process, then the final temperature is lower than the initial temperature, then you will register a negative delta T, which is not desirable. So that's why my advice is you do high temperature minus low temperature. And of course, knowing the final temperature, you should be able to tell whether the reaction is exothermic or endothermic. Then later on, you can rectify your answers. After all, positive and negative is not concerning about the magnitude. It's concerning about whether it is endothermic or exothermic. Okay? So just to make sure you get a positive value. Okay? Now, let's just give you an example. Now here, very simple experiment. You can just look at the diagrams. We have 100 cm cube of water. To that, we have thermometer and a stirring rod. And to the water, we will add in 16.4 grams of calcium nitrate. And the water initially is 24.8 degrees Celsius. After adding the solid, we stir. Okay, make sure all the solid has been dissolved. Then at the end, of course, we will have a calcium nitrate solution. And after that, we register 28 degrees Celsius. So obviously temperature rises after adding the salt. So when the salt dissolves in water, obviously the process is exothermic. It releases heat. Okay? Now, if you look at the calculation here, so first of all, we will do the heat change. So Q equals to mc delta T. Now, the mass is 100 gram. And you may say, sir, isn't it 16.4? Huh? Isn't it 16.4 just now? Huh? Why are we putting down 100 grams? Now, again, because we are talking about the mass of the substance where we measure the temperature change. You just look at the thermometer. We actually stick the thermometer into the water rather than the calcium nitrate. Plus, the calcium nitrate has been dissolved. So how can we measure the temperature of the calcium nitrate again? So that's why the mass must be talking about the water in this case. Okay? But then you may say, sir, 100 cm cube, why is it 100 gram? Now, because you know that for water, the density is 1 gram per cm cube. Okay? You know that for water, density of water equals to 1 gram per cm cube. So that means 100 cm cube is exactly 100 gram. 100 cm cube of water is exactly 100 gram. Okay? Now, this is the specific heat capacity of water, 4.2 joule per gram per Kelvin. Then you may also argue, hey sir, you see, not water, it is calcium nitrate solution, not pure water, right? Now, this time you are correct. Yes, there is actually a difference between the specific heat capacity of pure water and calcium nitrate solution. But for simplicity's sake, again, we don't want to make things too complicated. So the blue part here. Similarly, it is assumed that the specific heat capacity of calcium nitrate solution is the same as pure water for simplicity's sake. All right? But of course, knowing this fact, knowing this assumption, this is actually one of the errors that we will come across in this kind of calorimetric experiment. Okay? So you need to recognize that this is actually an assumption. Okay? Now the delta T, we do high temperature minus low temperature, and you tap your calculator, you find out Q equals to 1,344 joule. Okay? So the heat released is 1,344 joule. Now you see here, I put down this sentence is to tell people that this is an exothermic reaction. Okay, it releases this quantity of heat in this experiment. Okay. Now down here, enthalpy change. Now remember, for enthalpy change, we are concerning about per mole. per mole reactant or product? Well, based on what kind of enthalpy terms that you are talking about, but most importantly, per mole. So that's why delta H equals to Q over N. We want to divide the number of mole. Okay, so basically it means like, okay, in this experiment, we actually using 1 mole of the reactant. Now here, 16.4 grams. Do you think it is exactly 1 mole? Well, we can simply using a calculator. So calcium nitrate, the molar mass is 14.1 plus nitrate is 14 plus 16 times 3, altogether times 2. So 164.1. So then we have 14.4 divided by answer. Actually, it is 0.0999, so 0.1 mole, right? 0.1 mole. So from that, you will be able to tell. Maybe I put it here. You know that 16.4 grams is able to give us 1344 joule, and which is basically 0.1 mole. That can give us 1344 joule. Now we want to do per mole, right? Per mole. So my question is, what about 1 mole? So how much heat can be released? So to do that, we will have the heat divided by the number of mole. So that's why we have the delta H equals to Q over N. Okay, this is how it works. So over here, delta H equals to Q over N, so Q over mass over molar mass, which is this one, then at the end you will get this 13,440. And you see here, negative. Suddenly it becomes negative. The reason is because now we are talking about enthalpy change. For enthalpy change, we have positive, we have negative. Again, it is not talking about big or small. It's talking about endothermic or exothermic. Because you know that this reaction is exothermic, right? So that's why over here, we will put down the negative here. It's perfectly fine, okay? So, so you see there is a negative value, and also you get this huge number, negative 13 something, because it is in joule. But for enthalpy change, you need to use kilojoule. So at the end, you need to divide it by 1,000. Then you will get this negative 13.4 kilojoule per mole. Okay? And this is actually the enthalpy change of the dissolution of calcium nitrate. Okay? Dissolving calcium nitrate in water is exothermic. Okay? So that's the idea. Okay? Now, here, some common source of error. Now, that one would be very useful when it comes to doing experimental reports, because very often they will ask you about the source of error, ways of improvement. This is a good example to illustrate that. Now, usually, you see the literature value. It is negative 19 kilojoule per mole. So that means, comparing to this answer, actually, the dissolution of calcium nitrate is able to release even more heat. So the solution should be hotter than just now what we have measured. So that means some of the heat released is lost, is gone, is wasted, something like that. So we want to find out what are the source of errors and how we may be able to improve the result. So first of all, this is very common, heat loss to the surrounding or heat gain from the surrounding. It depends on whether you are doing exothermic reaction or endothermic reaction. If you're doing endothermic reaction, you may have heat gain from the surrounding. Okay? Heat loss to the surrounding. So how does it affect the enthalpy change? Well, if you have heat loss, then obviously it will lower the maximum attainable temperature, right? So for exothermic reaction, okay? Of course, it will lower the maximum attainable temperature. So in this case, we have 28, but maybe theoretically it can climb up to 30. But because of the heat loss, it can only reach 28, okay? So this is the idea. What about endothermic reaction, which is a little bit rare, okay? A little bit rare. Now, in this case, we will have heat gain from the surrounding, that it will raise the minimum attainable temperature. Do you get that? For endothermic reaction, as the reaction proceeds, the solution should get cooler and cooler, probably cooler than 25 degrees Celsius. So maybe theoretically it can cool down to 20, but because of the heat gain from the surrounding, heat is transferred from surrounding to the solution, then it turns out that it only reaches 22. So this time it is heat gain from the surrounding. Okay? Now here, the specific heat capacity of apparatus is neglected. Now here we assume that only the 100 cm cube water will absorb the heat released from the dissolution. However, the beaker, the thermometer, the glass rod, so all of these apparatus, they also have a specific heat capacity. They will also absorb heat. So part of the heat released from the process is absorbed by the apparatus. So that's why there will be fewer or less heat absorbed by the water, and therefore the maximum attainable temperature again is lowered. Okay? Similar idea for endothermic process. I do not repeat myself too much. Now here, incomplete reactions. So reactions obviously could undergo incompletely. Maybe you didn't stir it thorough enough, so some of the salts still remain undissolved. So in this situation, let me talk about the others. So like, for example, impure reactants, like you are having the calcium nitrate, but they are not 100% pure. You could have having some calcium oxide inside or calcium carbonate, which is insoluble in water. So it may result in less heat being released, or in a very rare case that the impurity actually release even more heat, but very rare. Usually the impurities will result in releasing less heat. Okay? Also, if your reactant is volatile, in this case it is not the case. The salt is involatile. But if you come across with volatile reactants, then during the transfer of reactants, part of it may be lost due to vaporization. So this is also one of the considerations. Now all of these, 3, 4, 5, again, will result in less heat being released. Okay? So it will again lower the maximum attainable temperature. All right? So you notice all of these errors, most of the time these errors will result in an underestimated result, underestimated experimental result. For most of the experiment, you will have an underestimated result because of the heat loss. It should have given more heat than it's supposed to be, right? So that's the idea. Now, very quickly, we have a practice question. Again, you know the drill. I want you to pause the video, attempt the question, and then we will check. Okay, let's do it. So now we are again dissolving a salt in water, and we want to find out the enthalpy change of the solution. So here, this time it is ammonium chloride. We have this gram of ammonium chloride, this quantity of distilled water. Yeah, basically the same thing. We have the initial temperature and the final temperature. Now you notice the final temperature is lower than initial temperature, implying that this dissolution process is endothermic. So the delta H at the end should be positive. Specific heat capacity of water is given. Now here, using an ionic equation, including physical state, for the dissolution of ammonium chloride in water. Ionic equation. So this one, as it dissolves in water, it will form ammonium ion and chloride ion. Okay? Aqueous. Suitable glassware to measure 200. So actually here, you may suggest pipette, but pipette is not really a good choice here because we have to measure like a couple of times to get a 200. And here, we are not actually requiring a very accurate measure of the quantity of water. So here, measuring cylinder should do the job. Measuring cylinder, okay? C. Explain briefly how the student know if all ammonium chloride powder had been dissolved in step 5. So step 5 here, the temperature of the mixture was measured when all ammonium chloride powder had dissolved it. So how can he tell? So of course, you can tell by two methods. One is when you no longer see any white solid, okay? So when no white solid is observed in the water. This is one way of doing this, or you can say when the temperature of the solution stop rising, stop dropping. Because this time it is endothermic, so it should be dropping, right? So both methods would do. Now from the information above, calculate the heat change, which is Q. So Q equals to mc delta T. The mass here, remember, we should not put down the mass of ammonium chloride. We should put down the mass of distilled water, okay? So 200 gram. Now C is given from the box here. 4.18 gram, joule per gram per degree Celsius. And delta T, remember, we want to have a positive number, so we do this one. Okay, 24.6 minus 19.8. Okay, and then we will tap the calculator, of course. Okay, so this is what you get. But this is in joule. Okay. Now part E here, based on your answer, calculate the enthalpy change in kilojoule per mole of the dissolution. You need to use the delta H equals to Q over N, right? So Q is this one, and the number of mole is mass over molar mass, which is equal to, now I can change this one into kilojoule first. And mass here we do 21.4 gram divided by ammonium chloride 14 plus 4 plus 35.5, which is this one. Okay, and at the end we should get 8.80 positive kilojoule per mole. Okay? Positive 8.80 kilojoule per mole. Okay? Now, the literature value here is positive 14.4. So this one is larger than what we have calculated. So that means the reaction should absorb even more heat than we have measured. Now calculate the percentage error. Now percentage error is calculated by the difference of our experimental value and the literature value over the literature value. Okay, so which is 14.4 minus 8.80 over 14.4 times 100%. Okay. So we have like 38.9% error. Okay. And lastly, two sources of error that accounts for the percentage error. So it could be a lot of the possible situation. We can have heat loss, heat gain. Okay, this time heat gain from the surrounding. We can have the specific heat capacity of the apparatus. is neglected, we can have incomplete dissolution. Now, but this one may not be that good because from the question, you have to pay attention to the wordings of the question. You see, it has mentioned that all ammonium powder has been dissolved. So in this case, we will assume that we have tried our best to make sure all the ammonium chloride powder has been dissolved. So we can't, again say that it is the incomplete dissolution. Now this one may not be a good choice. So we may probably say that the ammonium chloride is impure. That one may be better. Okay? So that would be some possible answers. Now, I'm going to stop it here. Bye-bye.